Hi, good morning, everyone. Welcome to the webinar Geometric and Physical Optics Simulation with Ansys. We'll wait 1 more minute for more people to join, and then we will start. Okay, so if everything is going well, let's start this webinar. So welcome everybody to Geometric and Physical Optics Simulation with Ansys. Let me go to the first slide, which is sort of introduction to the GoToWebinar environment. As you can see on the right, you have a side panel where you can change all your audio settings and your video settings. You won't be able to unmute yourself, but at the end we will enable that. So when you have any questions, you can also ask them live. During the webinar itself, there is a questions pane in the side panel where you can just type your questions and we will go over them at the end of the webinar. The webinar will take approximately 1 hour. The webinar will also be recorded and will be sent to you together with more information after the webinar. You can also, minimize the side panel by pressing the red button. So today we're going to talk about optics, of course. There will be 2 speakers, Morgan, who is the infinite sales overlay of optics, and Ekim, who is our specialist in optics. He's our application engineer for optics. But first, let me give you a short introduction on Infinite itself for those who may not know who we are. So Infinite Simulation Systems has already been around for, I think, more than 30 years. But since a couple of years ago, together with our sister company, Inoptis, we are now a group called 4ITGO. We share somewhat the same business and come in contact with a lot of the same companies, and therefore, really help a lot of companies with their complete production and process cycles. And it's a very good way to exchange knowledge between those 2 companies. We are located in the complete of Benelux, or we are active in Benelux. So we have actually 2 main offices, one in Breda and one in Sint-Alois-Winkel. And we also have a co-working space in Leuven, which means that from these 3 offices, we are able to access, let's say, the whole of Benelux quite easily. Our team is growing quite exponentially. We are now already with 70 team members, but we're still growing each year. And we serve almost 800 customers as of today, but that's also still growing. So I mentioned something about Infinite and Inoptis. Well, Infinite will most likely guide you with the most advanced simulation solutions that are available. And we do that together with Ansys, of course. We really want to know how your workflow is going, how simulation can be implemented in that to make your workflow the most efficient as possible. Our sister company, Inoptis, they really look at the complete process from implementation or design to really the end at production and putting it into place and services. They work together with PTC, which involves everything regarding CAD, CIA also, augmented reality, Internet of Things, a lot of things that really can make your complete cycle more digitalized. So I mentioned it before, we are already 30 years in the field, so we have been an official channel partner of Ansys also for almost 30 or for more than 30 years. We are actually also the only channel partner in the Benelux, which means that we have a very close relationship with Ansys. Our own support team, our own application engineers, they have quite a lot of experience. We have a lot of clients or customers that have been working with us and Ansys for already quite some time, which means that we have quite the experience and innovation to really help every kind of company. Let me go to Morgan, who will tell you more about the Ansys side.
Thank you, Sarah. I propose that we launch a poll first to know a bit more in which fields you are working. So I'm launching this poll. I let you answer just for 1 minute. Can you see the poll?
Yes.
Okay. All right. I see it's still moving. So, okay, seems to be converged. Simulation converged. So I close the poll. Yeah, so we can see that we have 10% of the participants involved in photonics. We have 20% involved in lighting, 30% involved in sensors, and 40% in other fields. All right, so let's switch to my presentation. You made me presenter, Sarah?
Yes.
Okay. Okay. So if I do like this, I swap the slides and I share my screen. Can you see my screen?
Yeah, we can see it perfectly.
Super. All right. So what should we do? What should we use simulation? Well, that can be because we have an issue or a problem we want to solve. For instance, we may have problems to meet standards that are required to put a product on the market. But we also may want to improve the product performance and reliability. Or maybe there is a problem for which we want to find the root cause. And also quite often it's fine that people want to use simulation because they have too high development cost and time. But in other words, no, you were not seeing my slides actually. Yes, you are seeing my slides?
Yes, yes.
Okay. Which slide are you seeing now?
Why do we simulate?
Yeah, okay. Okay. It's the one I wanted to present, so it's okay. So yeah, so it's about regulations, performance and reliability, root cause analysis, or reducing the time of development and its cost. Then, in other words, we can also see simulation as a way to drive innovation and to manage the complexity, but at the same time, to minimize the time needed to develop a product and put it on the market and to reduce the development cost. It's also useful to increase the quality of the product and to diminish risk. Now, why should you be comfortable collaborating with Ansys? First, it's because Ansys it's a company that is involved in simulation since the 70s, so more than 80 years actually. Simulation is the only thing Ansys is doing, so developing and supporting and support for simulation software with 40,000 customers worldwide. Also, even though it's one of the first companies involved in simulation, Ansys is continuously addressing new engineering challenges, notably thanks to a quite very good strategy in terms of company acquisition. About 30 acquisitions were done, I think, over the history of Ansys. And one of the last one is Zimax, of which Ekim will tell you more about it. So Zimax was acquired by Ansys end of 2021. Now, if we look at the full portfolio of simulation software that Ansys provides, so we have today about 85 products, which, when relevant connections between these products were developed to make them work together, which makes Ansys the leader in multi-physics simulation. So if we look at the bottom of this slides in the physics-based simulation ribbon, we can see that Ansys can be used for performing simulations for structural and fluid dynamics, also for electronics and electromagnetics, semiconductors, and of course for optical simulation, which is the topic of today. In terms of optical simulations, Ansys has 3 software to tackle this topic, to perform simulation from the nano to the macro scale, and Ekim will tell you a lot more about it. So yeah, I'm gonna stop presenting, and we'll give you the right, Ekim. If I manage to find back this thing, okay. So attendee tag. Okay. Hop, I give you the right, okay. Okay, make presenter. Yes. Excuse me, I'm not yet completely familiarized with the interface of GoToWebinar. So I give you the floor, Ekim. Maybe before that you start your presentation, maybe you can put your slide in full screen, and we can start a second poll to know a bit more about what your company is doing in optical simulation today. So I'm launching this poll, and then we'll review it afterwards. So I will let the poll for 15 seconds, something like this, 30 seconds. Simulation is converging. All right, let's stop the poll. So I can see from my side that we have 90% of the participants that are experienced in optical simulation, so which is a quite significant number. Yeah, and then we have also almost half of the audience that already heard about the different software that Ansys has for optical simulation, so Zimax, Spios, and Numerical. Yeah, that's okay, good to know. So Ekim, you have a team of experts in front of you, so I let you dive in the details.
Yeah, so you can see my screen clearly,
yes,
right? Okay. So most of you know, or maybe you don't know, that optics and photonics are all around you. So in your pocket you have a smartphone with a camera in it, and this camera gets better and better each year. In the medical field you have all kinds of devices that use optics to monitor what is happening inside your body. And for example, in the automotive industry, head-up displays and LiDARs are becoming more and more important. So to cover the whole range of optical simulations, which is very important because this technology gets more and more complex each year. And so you need to reduce the costs of prototyping. So Ansys has the whole range covered. So we have first numerical, which simulates the propagation of light through microstructures. So in the photonics, on the photonics level. Then we have Zmax that simulates and evaluates the propagation of light through optical systems like stacks of lenses or mirrors. And then we have Ansys Pios, which simulates the propagation of light as a ray through big environments like rooms, cars, streets, anything that's big. And so in this presentation, I will show you some examples of what this software is capable of doing. So let us start with sequential ray tracing. So what is sequential ray tracing? That is ray tracing when light follows a predefined path from surface 1 to 2 to 3 and so on. And this is mostly used for optical imaging systems like microscopes, telescopes, but you can also think about things like beam expanders or optical waveguides. So Zmax is a software in which you can design a stack of lenses, like you see in this example. You can assign all kinds of materials to it and give exactly the curvatures and the distance between the lenses. And then you can use Zmax to analyze your stack of lenses. So using, for example, these the Ray-Fan plots, you can analyze the aberrations that are present in your system. You can also just use spot diagrams that says at which position on the image plane the spots land, the light rays land. And also this you can use to get the aberrations in your system. But you can also just easily use Seidel diagrams. So Seidel diagrams tells you what kind of aberration is present at which surface in your stack of lenses. So we see, for example, that at surface 2 and 5, there is a lot of undercorrected distortion. But this is compensated by overcorrected distortion at surface 7 and 10. So, and in the end, at the image plane, there's not so much distortion anymore. You can also just make easily MTF plots, which give you information about the resolution of your image at the image plane. Of course, you can also just quickly simulate the point spread function, which also gives you information. And if you want to discuss your optical system with a person that is not specialized in optics, you can just simulate an image. So if there are any aberrations present, then you can easily see it here and explain it to your, for example, customer. So after analyzing, you can optimize your stack of lenses. And how you do that is that you define variables in your system, like the lens curvatures and distance between the lenses, and you make a merit function. And when the merit function is low, that means that your system performs optimally. So Zmax will make random changes in your system so that the merit function becomes low. In this case, we found a local optimum, but if you just keep the software running, it will keep running until you say to stop it. Maybe at some point it will find a global minimum. So yeah, so Zmax, you can easily use Zmax to optimize your system and find the best performance. Tolerancing. So no optical system is perfect. There are always little problems in it. So for example, your lenses can be misplaced, they can be tilted, or they can have the wrong dimensions. And the question is not if this will happen, but how much. So with Zmax, you can see if the system still performs desirably when there are small problems present. Also, Zmax has an extensive catalog of materials. So there are lots of glasses from different manufacturers, and you can all compare them to each other using, for example, dispersion plots. So let us now go to non-sequential ray tracing. So non-sequential ray tracing is the opposite of sequential ray tracing. In non-sequential ray tracing, light can go in any direction. So for example, one light ray hits this surface first, but another light ray hits the other surface first. So there's no predefined order. And non-sequential ray tracing is used for things like modeling light sources or simulate human visions. So how would a human perceive its environment? Or for example, machine vision. So how does a machine with a camera see its environment? And for the human vision, it is maybe interesting to know that in SPIOS, you can easily change the age of the person that is observing, because as you get older, your eyes get worse and you will see the environment differently. So maybe you want to compare how a 20-year-old person would see its environment compared to a 70-year-old person. And for the optical sensor vision, it is interesting to know that in SPIOS you can easily change the weather conditions. So maybe some car with a camera in it performs well on a sunny day, but when you introduce rain, it does not perform so well anymore. So with SPIOS, you can easily test if everything works correctly. So making these kinds of human vision simulations is not something so that you can show nice pictures to your customer. No, this is really to avoid problems. So let's say that you have, for example, a design of a car inside of a car. Then you want to see if there are any annoying reflections on the windows or the metallic parts. Are the mirrors well visible? Is the dashboard and the screen, is it well visible? Are there no annoying reflections there? So that you want to avoid these kinds of problems. And that's why you do these kinds of simulations. So to illustrate that, I wanted to show this example of a simulation of a car screen. You see that the screen is well visible, except when sunlight hits that screen. Then we have a problem. Then we cannot see the half of the screen anymore. So by making adjustments to your prototype, you can get rid of this problem. Now the sun glare is gone. So what happened here? They added nanoparticles to the screen, and this solved the problem. So the simulation of the nanoparticle can be done in numerical, and then the scattering properties can be added to SPIOS, and then in SPIOS you can see how a human would perceive the screen with nanoparticles in it. Let us move on to illumination solutions. So a few decades ago, most illumination systems were simple light bulbs. But now with freeform optics coming up, those illumination systems become more and more complex, which makes it more and more important to do simulations to develop these kinds of things. And also these systems sometimes need to require strict, these systems have to fulfill strict requirements. And so it is good to know that with Ansys, with SPIOS, you can connect it to Ansys OptiSlang, which is the optimization software of Ansys. So let's say that you have a certain requirement, for example, that you want the brightness of your lamp to be very homogeneous. They can define some variables in your prototype, and then OptiSlang will automatically adjust those variables until it has found an optimum. Let us look at another example of an SPIOS illumination simulation. So this is a simulation of a project in which they want to illuminate the inside of a train coach with UV light to disinfect the coach. Because as you might know, UV light kills viruses. So this robot moves inside the coach and has light on his arms. So with a simulation of SPIOS, you can evaluate if it works well. So at the first prototype, you see that the chairs on the inside are well illuminated, but at the side and the back not so much. With a second prototype, it got even worse. But then at the third iteration, you see that all the chairs are nicely illuminated and disinfected. With SPIOS, you can also diagnose problems easily. And to show that, I wanted to show this example. So this is a prototype of some sort of simple dashboard with buttons on it, and these buttons have lights. So here's a light source, and here's a scattering material, and then light comes out of this. But there is a problem with this prototype. If we put a sensor in front of it, you see that there is this weird glare around this. That bluish part that you see here should not be there. So let us look where the problem is coming from. On the sensor, we select the area with the problem on it, and then we see all the light rays that end up there. And we see that those light rays all come from the chamfer here at the button. So by making adjustments to this chamfer, we can easily get rid of this problem. So with SPIOS, you can easily diagnose your problem and make adjustments to it. Let us move on to photonics. So photonics has applications everywhere, like in LiDARs and in AR, VR systems, where you have meta surfaces and meta lenses. Those are not the lenses that you usually see, but they have microstructures in it. So to simulate that, you need numerical. Another example is, for example, in the quantum field, you have quantum computers that use photonic integrated circuits. So to do all these kinds of simulations, we have numerical, which is a wave optics solver. So light is simulated as a wave that goes through a microstructure. And in the numerical, you can do both simulations in time domain, like you see in this animation, but you can also do it in the frequency domain. So I wanted to show you a little workflow of numerical as an example. We will quickly design a CROW filter. A CROW filter stands for a coupled resonator optical waveguide. So first in Ansys, in numerical mode, we will design the waveguide and find the eigenmode of it. And then we will do two simulations in Ansys Interconnect to find the coupling coefficients and to find the needed voltage that we need to apply to it. And then in Ansys FDTT, we will find the distances between the waveguides. So first of all, what is a CROW filter? A CROW filter is just is like the animation that I showed before, but then with two rings instead. And you can also apply a voltage to it, but I will show that later. So in the input, you get light comes in, and then you have two outputs, which we'll call the true and the drop. And you can also add more light to it at the add gate. So we need to determine all the parameters, like the coupling coefficients K1 and K2, and find the radiuses of these rings. So first of all, in numerical mode, we design the waveguide and we find the first eigenmode of it. There we see quickly that the effective index of refraction is 2.57. So we want to design a filter with a free spectral range of 79.5 gigahertz. So when we plug in this value here, we find that the needed radius of the rings is 154 micrometers. Then next, in numerical interconnect, we sweep along different wavelengths. And then we see that the coupling coefficients, we can read it here, from the gain and from the two gains, we can see that coupling coefficients are given by these values. But there's a little problem. We see that the peaks are not at the desired wavelength of 1550 nanometers. So we still need to shift this. And we do this by adding a voltage. So we sweep along different voltages. And we see that the desired voltage is 0.95 volts, because then the peak shifts to the desired wavelength of 1550 nanometers. And lastly, what we need to do is we need to determine the distances of the gaps so that we get the required coupling coefficients K1 and K2. So we sweep along different gap distances, and we find that that it's about 410 nanometers for the straight to the band waveguide, and it's about 630 for the band to band waveguide. So I showed you some examples of the modules in Lumerical, but there are many, many more modules there. So we have different kind of FTTT simulations that can simulate the propagation of waves. If electrical charges or currents are involved, then we can also do it with the Lumerical charts module. If you need to even add heat to it, you can do it with the heat simulator. And if you have optical quantum optics simulations, well, there are some modules to do that as well. So let us move on to the next example, which is the design of a camera. So when people think about camera design, they mostly think about Zemax. But did you know that the other software also can have a contribution to the design of a camera? So for example, let's say that we have a camera system on a conveyor belt in some factory, for example. This camera monitors the products on the conveyor belt. Then we can use SPIOS to simulate the light, the LED light on the camera and the whole environment. We can use Zemax to design the lenses in the camera. And lastly, we can use a Lumerical to design the sensor in the camera itself. So how you do that? In Zemax, you can design your stack of lenses and then export and then do simulations on it, and then export the data as a black box to SPIOS. So in SPIOS, you won't see all the lenses, but all the performance of the stack of lenses will be exported to SPIOS. And then you can simulate how the camera would perceive the products on the conveyor belts, as you can see here. So what about the Lumerical part? So in Lumerical, you can make a simulation of how the light hits the light sensors. And then you can extract a BSDF that says how the light scatters off of this surface. So you can import the BSDF as a file to SPIOS and add it onto the surface. So instead of making the microstructures in SPIOS itself, you can just make it flat and just add this BSDF here. And then you will see that that this camera has a problem in it, because you see that there are these glares. And these glares are caused by the microstructures of the sensor. So these glares that you see here, you cannot simulate this with SPIOS or ZMX alone. You really need a Lumerical for this. So we have seen that there are many examples of projects where all the three softwares are combined, but we can go even further. We can also do mechanical simulations on the optical systems. So let us move on to optical multiphysics. Let's say that, for example, we have a lens system on a car, so a camera on a car, and this camera performs very well at 20 degrees. But when the sun shines on the camera and it heats up to 70 degrees, the image becomes very blurry, unfortunately. So what we can do is we can redesign the lens. So now at 70 degrees, it still performs reasonably well. So what just happened here? We designed the lens and then we did a thermal simulation on this. And so when we add heat to the camera system, it will deform. There will be strains in it. And so if the shape of the lenses change, the performance of the camera will also change. So we did a simulation and we added it to SPIOS to see what the result will be of these deformations of the lenses. Another nice example is that we can combine Ansys Fluent with optic simulations. So here we have a car with a camera on it. With Ansys, we can do a rain simulation. So some of the rain falls directly on the camera, some gets kicked off by the vehicles around it. And then we have droplets on the camera, and then we can simulate if the image quality is still desirable. And doing these kinds of simulations is not some sort of unnecessary luxury, because as you can see, droplets can hide whole objects. You see there are three pillars here, but when you add droplets on the camera, those pillars are not visible anymore. So doing these kinds of simulations is very important. And also we can add dirt to the camera. So in this case, luckily, well, the pillars are still visible. And lastly, I wanted to show you quickly the workflows of VR, AR, and LiDAR, because Ansys has end-to-end workflows for these three things. So for AR and VR, you can, of course, just design the stack of lenses in Zemax. In Lumerical, you can design the gratings, so the meta lenses, and they can all add it together in SPIOS to see how a human would look through this AR or VR glasses. And for LiDAR, we have end-to-end flow. So a LiDAR that emits a laser, you can simulate the optics. The laser will hit a scene. So for example, another car which can be simulated in SPIOS. The signal will be returned, and that is collected again by optics. The camera can be, the camera sensor can be done in Lumerical, and also the signal processing can be done in Lumerical and HFSS. And then after that, yeah, so the data can be synthesized, which can also be done in SPIOS, and then you can use Ansys to train your computer vision algorithms, because you want to have a software that can make decisions for your car. So there are a lot of examples. I cannot show everything here, of course. So I can understand that you have some questions, maybe some things on your mind. So now is the right time to ask your questions.
Thank you very much, Kim. That's very, very interesting. Maybe just before that we start answering potential questions, I'd suggest to launch a little poll that's in the meantime, people can explain us if they have like new kind of optical simulations they'd like to perform. In the meantime, they can reflect on some questions, and then we can answer them. But thank you, that was very interesting, Kim. Let's see a couple of seconds. All right. Thank you very much. So, is there any question for Kim or for me from the attendees? So maybe what I can do is maybe to
and otherwise, you can always send an email afterwards to the emails.
Yes, of course, of course. So you can put your question in the chat if you want, or I can also unmute everyone, and then you have the capacity to unmute yourself then. Okay. So your explanations are too clear, Ekim. I have to admit it was very well presented. So thank you very much. And if there is no no question for you, then I propose that we close this webinar. Of course, we will send all the slides and the recording to the attendees. Are people interested in that? Yes. I wish you all a very good day and good simulations. Bye bye.